Our topic is data structure, file organization, and physical database design. That's the concept, right? Data structure, file organization, and physical database design. What do we mean by data? What do we mean by data structure and file organization? That is most important. Now, data is prerequisite of any system, any processing, right? Then where we are going to put our data, so that's basically called file, and where we are going to put our file, that's called folder. Now, how we are going to organize it and how we'll put into the surface of the hard disks. That's the concept. Probably Anu has a better idea in data structure because he has done BCA, right? Now, in this chapter, what exactly we are going to learn, the definition and basic concepts, why database structure, memory hierarchy, RAID technology, RAID technology, index, binary search, data structure, linked list, inverted list, B-tree, file and their organization, file storage concept, sequential access model, indexed sequential access method, direct access method, physical database design. These are the concepts we are going to learn in this chapter. So let's have a look why exactly the data structure is. What is the need? So we can see this movie.
Everyone accepts on some level that getting organized is a good thing, or at least recognizes that being disorganized will work against you in some way or another by the value of chaos. But when we look closer in our day-to-day lives, we all have established some level of order on the things we use. Knives and forks are near or inside the kitchen. Toothpaste is close to the place where we brush our teeth, and the keys to the car are more likely kept in a contained number of places. If our lives don't have enough order, it would be difficult to even get out of our beds. And as the number of things we are dealing with increases, so does the need for a structure to hold it together. Inefficient systems drain energy, and that's true for the world of computing also. Computer applications also store and process information. And given the changes in the amounts of information available to us these days, applications face an increasing need to organize data. To begin with, here is what you really need to know about data structures. Data structures are all about how data is stored in memory and various operations that can be performed on that data. Now, different data structures have different ways of doing this, but generally it is either by linking, ordering, or grouping similar items together. Further into this series of videos, we will look at how various data structures make use of these general strategies to organize the data. Right choice of data structure can help you build inefficient code that is difficult to implement and maintain to a new level of clarity and conciseness, to a code that not only executes fast but also takes less memory space. This is it for an introduction. Next, we will take a look into best ways to explore data structures with insights that you won't find in any of the books or courses online.
Now, we have already seen data structure. Huh? So what happened when you were creating a database? So you are going to create a different kind of container where you are going to put the data. So here the container you could tell the table, right? So every table has its own data. Suppose book has its own data, and the publisher has its own data. Member has its own data, and those data are related data. When we are asking for the book data, so definitely it's all about the book, the different elements of book data information and the data. Where it is member is concerned, it's a member and the different element of a member data, that means name, roll number, address, etc., etc. When so two are different concepts. When we the concept for the publisher data, so importantly, normally we call this imprint the information when it's come into the catalog. So there you will find that it's a name, address, phone number, places. So these are the important aspect of a data structure in a library system. This is a schema diagram for creating a library automation databases. Here you can see the book ID is connected with the author in the author table, library branch, book copies, borrower, and book loan. So book ID is connected with almost everywhere, right? Almost everywhere. Now, there are some linked concepts. So data structure means there is a one data, how you are going to communicate with the other component in your databases. That is the complete concept of your data structure. Now, why we create data structure? Because the key factor of designing data structure and file organization is the relatively slow speed in hard disks. What happened in the hard disks? Suppose there is a hard disk, and hard disks always take data in a either in a bit 1 and 0. So it's become a bottleneck in the hard disks. So whenever we're putting some data, it goes directly to the hard disk. So it's create chaos in the line. So we require a kind of system which can communicate to the hard disk by in a sequential order. So if you do that one, suppose something is coming in your database and you are taking everything in your databases, and that when you are taking free time, when your hard disk is not going to process, so data is going to a hard disk simultaneously, right? So that's why you will not you will not able to find any kind of traffic in the data process, data communication, right? So data structure that's focused on minimizing disk access on the maximum likelihood. That means whatever work you are doing in the databases, that will be on the software. So at the end of the refined data can be put into the hard disk. So these are the basically and other thing is a logical way how you are processing the data. Your hard disk cannot do all processing. So you need to have a very intelligent kind of system which can process the data, whatever you require. So you have to structure on that way that can carry forward for the processing of the data. So that's why data structure is very much important in compiling a database in a computer system. If you look at the memory hierarchy, we'll see how memory hierarchy working. Now, this is a level 0 when CPU register. Normally, you will see when you are doing something on your computer, so everything taking out by the CPU register. Then cache memory is whatever work you are doing, it is going to the cache memory, right? So sometimes in your mobile phone also, you'll see you are just pressing for the clearing the cache memory. That means whatever past work we have done and that is into the cache memory, that need to be deleted. So your memory will be little free. So later you can start working on that, and your cache memory can take the new task. Then main memory is a concept of memory, then magnetic disk or optical disk or magnetic tape. So one by one, in next level, you will see the memory hierarchy. Here, super fast, super expensive, tiny capacity, the processor. Then SDRAM, DDR, faster, expensive, small capacity. Then physical memory, fast, priced reasonably, average capacity, SDROM, DDR, SDRAM. Then average speed, priced, reasonably average capacity, solid state memory, then slow chip, large capacity, magnetic hard disks. So these are the capacity of your memory in a computer. So why exactly we're doing the database structure to create a kind of communications between the CPU to cache memory to physical memory. So when you are managing these things in a methodical way, then the accuracy of your data processing begin very high. And not only accuracy, the speed of data processing is gone level higher. So that's the concept. Here we can see the how hard disks and the data the memory RAM and hard disks how hard disk is processed.
Hello everyone. In this video, we're going to talk about one of the most important parts of a computer, and we're going to be talking about primary memory or temporary storage. And this is called RAM. RAM stands for Random Access Memory. RAM is stored on the motherboard in modules that are called DIMMs. DIMM stands for Dual Inline Memory Module. A DIMM is a dual inline module because it has two independent rows of these pins, one on each side. A DIMM memory module has either 168, 184, 240, or 288 pins. And then the DIMM is installed on the motherboard in the memory slots. A motherboard can have a various number of memory slots. The average motherboard will have between 2 and 4 of them. In order for data or a program to run on a computer, it needs to be loaded into RAM first. So the data or program is first stored on the hard drive. Then from the hard drive, it's loaded into RAM. And once it's loaded into RAM, the CPU can now access the data or run the program. Now, a lot of times, if the memory is too low, it might not be able to hold all the data that the CPU needs. And when this happens, then some of the data has to be kept on the slower hard drive to compensate for the low memory. So instead of the data going from RAM to the CPU, it has to do extra work by going back to the hard drive. And when this happens, it slows down the computer. So to solve this problem, all you need to do is increase the amount of RAM on a computer. And by increasing the memory, more data can be loaded into the faster RAM without the need of constantly accessing the slower hard drive. And the result is a faster performing computer. So this is why a computer with more RAM performs faster than a computer with less RAM. RAM requires constant electrical power to store data, and if the power is turned off, then the data is erased. RAM also comes in different types, such as dynamic RAM or DRAM. DRAM is memory that contains capacitors. A capacitor is like a small bucket that stores electricity, and it's in these capacitors that holds the bit of information, such as a 1 or a 0, because that's how computers read data, which is ones or zeros. And because DRAM has capacitors, they have to be refreshed with electricity constantly, because capacitors do not hold a charge for very long. They constantly leak. And this refreshing is where we get the name dynamic. The capacitors have to be dynamically refreshed often, otherwise they will forget the information that they're holding. Another type of memory is called SDRAM, which stands for synchronous DRAM. And this type of memory is what is used today in RAM DIMMs. SDRAM also has capacitors like DRAM, but the difference between SDRAM and DRAM is basically speed. The older DRAM technology operates asynchronously with the system clock, which basically means that it runs slower than the system clock because its signals are not coordinated with it. But SDRAM runs in sync with the system clock, which is why it is faster than DRAM. All the signals are tied to the system clock for a better controlled timing. So as stated before, RAM is sizes. Today, they range anywhere from 128 megabytes to 32 gigabytes per DIMM. SDRAM is also rated at different speeds, but before we talk about the speed of RAM, we need to define some things first. Now, the term 64 or 32-bit data path refers to the number of bits of data that are transferred at a time or in one clock cycle. The more bits that are transferred in one clock cycle, then the faster the computer will be. Now, DIMMs have a 64-bit data path, which means that they can transfer 64 bits of data at a time. Now, prior to DIMMs, there was an older RAM module called a SIM, and SIMs had a 32-bit data path, which means they can transfer data 32 bits at a time. So that's why DIMMs are faster than SIMs, because they can transfer twice the amount of data per clock cycle, because DIMMs transfer 64 bits of data at a time compared to SIMs, which transfer 32 bits of data at a time. Now, a single bit or 1 bit of data is the smallest form of data that the computer reads, because in the computing world, a computer only understands ones and zeros, which is represented by a single bit of data. Now, there is also the term byte, and 8 bits is equal to 1 byte. So if a memory DIMM is rated to have a 64-bit data path, then that means that it has an 8-byte wide data path or bus, because 64 divided by 8 equals 8. SDRAM is rated at different speeds. For example, a stick of old SDRAM way back in the late 1990s could be labeled PC 100. The 100 equals the maximum speed at which it operates, which is 100 megahertz. And since SDRAM only comes in 64-bit modules, as we discussed earlier, it has an 8-byte wide bus, because 64 divided by 8 equals 8. So to figure out the total bandwidth of PC 100, we multiply 100 megahertz times 8 bytes, which equals 800 megabytes per second. So the total bandwidth of PC 100 equals 800 megabytes per second. So in other words, PC 100 RAM can transfer data at a maximum rate of 800 megabytes per second. So an SDRAM module labeled PC 133, you multiply 133 by 8, which equals 1066. So the total bandwidth for PC 133 equals 1066 megabytes per second. Now technically 133 times 8 actually equals 1064, but 1066 is accurate because the actual clock speed is 133.3333 times 8, which is rounded off to 1066. Another type of memory was called RDRAM, which was developed by Rambus Inc. And they developed the RIM, which stands for Rambus Inline Memory Module. RIMs have 184 pins and look similar to DIMMs, with the exception that the bottom notches are located in the center of the module. In 1999, RIMs were a breakthrough in the speed of memory, but has quickly fallen behind due to the advancement of technology in DIMMs. When RDRAM debuted in 1999, it ran at 800 megahertz, which was considerably faster than SDRAM, which ran at 133 megahertz at that time. But even though it was a lot faster than SDRAM, RDRAM only had a 2-byte wide bus, compared to SDRAM, which had an 8-byte wide bus. So if you multiply the speed of RDRAM, which was 800 megahertz, times the bus width, which was 2 bytes, you would get a total bandwidth of 1600 megabytes per second. As technology increased and processor and bus speeds have gotten faster, a new RAM technology was developed to keep up with the faster speeds of computers. This newer technology was called DDR, which stands for double data rate. And that's basically what DDR does. It sends double the amount of data in each clock cycle compared to non-DDR. Non-DDR, or single data rate RAM, uses only the rising edge of the clock signal to transfer data. But DDR uses both the rising and falling edges of the clock signal to send data, which gives DDR the ability to send twice the amount of data. So here is another illustration comparing the difference between DDR and non-DDR. So even though the system clock is pulsating at the same speed for both RAM modules, the DDR RAM module can send twice the amount of data since it takes advantage of both the rising and falling edges of the clock signal. So even if we speed the clock up and make it go faster, the DDR RAM will still send twice the amount of data compared to the non-DDR RAM. DDR is also labeled differently than non-DDR RAM. DDR RAM may include both the clock speed and the total bandwidth in its name. So instead of just including the clock speed in its name, like PC 133, where 133 equals the clock speed, DDR includes the total bandwidth also. So for example, a DDR DIMM labeled DDR333 PC 2700, the 333 is the clock speed, and the 2700 is the actual total bandwidth. So 333 megahertz times 8 bytes equals 2700 megabytes per second, which is where we get the name PC 2700. A new technology that has succeeded DDR is DDR2. DDR2 is faster than DDR because it allows for higher bus speeds and effectively send twice the amount of data than DDR. And it also uses less power than DDR. A DDR2 DIMM has 240 pins compared to DDR, which has 184 pins. DDR2 is labeled just like DDR, but with a small difference. For example, a DDR2 DIMM could be labeled DDR2 800 PC2 6400. And the difference is the 2 right after the DDR and the 2 right after the PC. So this is how you can identify DDR2 memory by using its label. And right after DDR2 is DDR3. DDR3 is twice as fast as DDR2, and it also uses less power than DDR2. And just like DDR2, DDR3 also has 240 pins, but the notches in the DIMMs are in different places. So you can't put a DDR3 DIMM in a RAM slot made for DDR2. In fact, motherboards are made to support a certain type of memory. So you can't mix DDR1, 2, 3, or 4 on the same motherboard. An example of DDR3 would be DDR3 1600, PC3 12800.
So you have got the concept that there is a RAM, there is a hard disk. RAM, you are increasing the power of RAM, DDR3, DDR4, but it is going again to your hard disk. It's faster speed. But importantly, I will tell you the writing speed of a hard disk is, it's remain almost same. It increased 20% per year, whereas the other technology increased 50%, 70%. So your capacity is increasing and the transfer mode is increasing, but the writing speed is not at par with the increasing quantity of the transfer rate or the RAM kind of concept. Now, what exactly the problem is, if you do not have a smarter software system, your hardware cannot able to read the data, and they are not going to sift it. Now, here there is a concept is redundant array of independent disks. Is a way of storing the same data in different places in multiple hard disks. You have seen in the hard disks videos that in hard disks is a different layer. In different layer, they're putting the data in a very smarter way that it could be accessible very easily. So that is one of the finest concept RAID technology. Now, how it works. Suppose you are spending some kind of data into the hard disk, it indexed, and at the same time with the index, it will start writing one by one. So it's a clever one. If you ask any any information, it take out and it will read sequentially and give back to you. That is the way it has worked. This is a RAID mirroring technology. Sometimes what happened, everywhere you will find the concept is mirroring. It's nothing. Mirroring is just keep one mirror in front of you. We are watching the same faces in the mirror. So everywhere, for the security purpose and for redundancy of the hard drive, you have to create mirror kind of thing, mirror space, right? It's almost similar. So when you creating mirror for the higher and faster data processing, data writing, data accessibility. So that's help the technology in many ways. That's why we are in a certain development we have done in the computer. Now, index. An index is a file which it's almost the concept of index in generally what we what do we mean in the index we're doing in a different last page of the book. It's almost like that. You are taking the data and you are creating some kind of index for the speedy data accessibility. Now here you can see this is a kind of index here. You will see the suppose Dhote. Now here A58 and his so you are creating index file in a minimum required data. So when you are searching, it will immediately goes to the index, and index will immediately take out from the actual index file. So that's the way you are getting information. Here you can see some kind of example on a different index. Here an example binary search to find out the Janardhan, find the middle and the last name of Gautam. Here this is the way it search and immediately it goes and it return back. So this is one binary search of the indexing system. Now coming to the data structure. In complete science, data structure is a data organization, management, storage, format, enables efficient access and modification. More precisely, data structure is a collection of data values, the relationship among them, and the function or operation that can be applied to the data. Think for a database, like suppose you are thinking for a database in a library system. In library system, what happened? When you are creating some kind of database for the circulation, you have to create one book database. At the same time, you need to create one member databases. And for transaction of the book or the circulation of the books, you need to create one transactional databases. And in transactional databases, you have to correlate with the book data and the member data. That's basically the organization. Whenever you require who has issued one book, so immediately you get access from the data structure in 3 different areas or 3 different tables. That is the way the data structure is required to do in a very methodical way. That's why it could indexed properly. And here you can understand the concept of data structure: linked list, indexed, inverted list index, and B tree. This is a basic concept on that data structure. Now, linked list, what happened? It's just linked one table to another table, or one data area to other data area. Suppose there is another example, probably. No, here you can see, well, this is not, I could have seen through application. I will show you in applications. I don't have access over here, otherwise I could have do. So just to think that, suppose every data has a one primary key. Every data element has its one primary key, or primary. Suppose the student has their roll number in the universal, and it could be assumed as a primary key. That could be linked with the transaction table. At the same time, when book data is there, so book data has its own universal or one key, which is exactly called accession number of the book. It's unique. It's universal. When you link together, and we're creating some kind of secondary data component, then it's come from both of the table. So that's basically kind of linked concept. Now, inverted concept is nothing. It's creating kind of list of data where it has inverted, it has indexed properly. So when you are searching something, it will come from the inverted list or the indexed file. So here you can see some of the example is that suppose digital computers, and here you are using DEC, then Ford Auto, your primary key is same, but in inverted or indexed file, you are keeping over here F. GM Auto, here GM. Intel computers, so you are keeping the records in a INTL. The primary key is always will be the same. Then Lockheed in aerospace, so you are creating L over here. So when you are searching something, it will immediately goes to that particular table, and it will give you the same result. So that's basically called inverted index file, index list. Now coming to the B tree, it's a binary tree. Probably you will get whole concept in B tree over here. It's nothing. Suppose there is kind of a hierarchy in the data level. Hierarchy in the data level. If we look at that video, probably we'll get some kind of information on B tree.
Hi, in this video I'd like to talk about B trees, how they can help determine what to index and what not to index in an SQL database. First, let's open any book at the end. This is the index, the section of the book that points out where important keywords are. So if you want to find the term, you can look up the pages that reference the term instead of going to the whole book. Similarly to that, we can ask our database to keep an index next to a table. And when we want to find something specific, instead of going to the whole table, we will use the index to help with our searches. How does this work? Let's get back to our table. If we store the table as a linked list, whenever we want to find an item, we would have to traverse the list until we find it. On average, we have to traverse half of it. And the more items we have, the more we have to look through. This is called linear complexity, or big O of n. Put simply, it means that the time it takes to look something up grows twice if the data set doubles. How can we improve that time? We can if we sacrifice in something else, for example, space. Let's try using separate structures to store where the data is. For example, a binary search tree. We can choose a root and put our elements before or after the root. Then, as our database grows, it's easier for us to locate an element, as we don't have to traverse the whole tree. Now, the time it generally takes to find an item doesn't grow that quickly. It performs in what is called logarithmic time. If the data set doubles, the search time increases by a linear factor. This is much better than list traversal. However, if we have more elements in one of the branches, we'll have an unbalanced tree. The worst case scenario, then, is that we still have to traverse all the nodes to get to the one we want. Can we do something about it? What can we sacrifice to optimize the search time? Well, we can trade off some time it takes to add items to the tree. Whenever we insert a new record, we can choose a new route in such a way that the height of the tree remains the same for all branches. There's one more practical thing to consider here. Disk access is expensive, so we want to do that as rarely as possible. To achieve that, we can store several elements per node in a sorted way. This is called a page. When traversing the tree, you access the disk only to receive the pages instead of individual elements. The page has a fixed maximum size. When you add a new element to the page and it becomes larger than the limit, the page needs to be split and the tree then rebalanced. This data structure is called a B tree. Balancing the B tree is a cost that we have to pay with every insert, but our worst case scenario still performs a logarithmic time. All right, so now after we've seen how an index tree is assembled, we can better decide what to index. For instance, if we add an index to a Boolean column, the tree will contain two large branches. The storage engine would still have to traverse lists of pages on the true and false signs. The index doesn't really help here. Or take another example. Let's say you add an index to a column containing very different data, like UUIDs or random numbers. It will result in a tree that has to be rebalanced often, since the insert goes to very different pages, causing them to split. So if you're doing more inserts on random data, perhaps a primary key B tree index is not the best one for you. We can also use this knowledge to look a bit closer at what we're indexing versus what we're searching for. For example, if we have a composite index on the first name and last name, searching for a concatenation of both will not hit the index. Or if we're indexing a datetime field, but are searching for entries using the date part, we will also not hit the index. Every entry has to be transformed before comparison. Keeping an index is a cost, and we have to make sure that we benefit from it. Whenever I design a table, I usually play around with indices and do an explain of most common queries that I expect. So that's it. In this video, we only looked at a B tree index.
Now, here you will see the B tree has started by the bare. Now, sometimes it's called balanced B tree. Now, how we are going to put information over there? It's nothing. Suppose you are inputting one data of a user in your library. Suppose that user must be a student or teacher. If teacher, then what is the stream? Suppose there must be a stream department. On the department, there must be a specific subject he taught, or a student. In one student is a complete, then in which class, in which section. This is the way it's create a kind of B tree kind of thing. So the data accessibility goes very high. Now coming to the file and their organizations, how we are going to organize the file. It's a very complex process, but at the same time, if you find yourself, it's very interesting also. The file sequence of a record, right? File is a sequence of record. File organizations refer to physical layout or structure of a record occurrence in a file. File organization determine the way records are stored and accessed. In many cases, all records are in a file are of the same record type. So when you are putting record in a place, so they are linked with. So you need to create some kind of structure where you need not to retype or re-input the data. So that need to be correlated. I'm just giving some kind of examples. When you are creating or inputting one vendor list or publisher in a book table, so you need to have a kind of drop-down menu. Now, on drop-down menu, you can list a kind of table from where you have already kept some name of the publishers, where you just press the 3 alphabets or 1 alphabet, it will create a kind of drop-down menu. We are selecting from that. So this is kind of concept of file storage. So look how file storage is working over here.
There are two types of file access mode. The first one is a sequential access. The second one is the random access. Let's look at sequential access first. Suppose I have a tennis ball can here, and we have 3 tennis balls, 1, 2, and 3. And now I'm going to put balls inside the tennis can. This is the first one, second one, and the third one. So you can see we have the tennis can full of 3 tennis balls. Now I'm going to take out ball number 1 from this tennis can. So what should I do? I need to take out ball number 3 first, and then the second one, and finally the last one, ball number 1. And in the process, we call this kind of ball access mode sequential access, because we need to take out the third one, the second one, before we can take out the first one. So this tennis can, this mode of access, we call this the sequential access. We need to take out the balls one by one. Therefore, you can see that the limitation of sequential access is that the access time, the time to take out the balls, for example, the first one or even the second one, is quite long, because you need to take out them one by one. You can't just take out ball number 1 from the bottom, because it's sealed at the bottom. So the access time or the seek time is long in sequential access. And the second mode of file access is direct access. That means the tennis ball are arranged in this way. So we have 6 tennis balls here. If I want to pick out ball number 3, I'll just pick it out directly. And we call this direct access. There is no need to take out ball number 1 and ball number 2 in order to take out ball number 3, because you can directly access or take out the ball, because there is no limitation in the order in which I take out the ball. So it's quite simple that this is direct access. And the main advantage is that the seek time, the time needed to take out one ball, is shorter, at least much shorter than sequential access. Remember? So the tennis can, this one is a sequential access. And this one is a direct access.
Now we could understand we have, when we think of creating file structure, we have a sequential access method. So you have already seen that in sequential access method is putting one by one into the disk. So when you are going to access, so you need to take out the last one, then you have to go to the first one. So that's the complexity in the sequential access method, where this is a sequential access method, one by one. When you are thinking of 8, so you have to, thinking of 4, you have to take out the four things, then you have to come to the 4th one. So it's a time consuming in sequential process. Random is chaos. Random is chaos, because sometimes it's difficult to find out where exactly the location is in random access. But when you talk about the direct access, probably it will be much better opportunity, right? So index sequential method, index sequential file recorded occurrence are sorted and stored in order by primary key. When data is keeping in the hard disk or in the table. I'm always talking hard disk. It is not the hard disk. It is on the table. So where we are putting the data, right? So in indexed sequential access, it's very, very interesting that you are just searching, just taking the data through their primary key. Primary key means one unique key. As a student has a roll number, it is unique key. Books has a unique number, accession number. So if you create a kind of table or databases on the basis of the primary key, so their index sequential access method is much faster and accurate. So today's date, probably everybody are using through this process, right? Now, this is a kind of index file and key value and data. We'll do it practically. So you could here some example. This is index. This is the primary key. right? This is basically a logical record. This is track 1, track 2, track 3, and you are asking one information, so immediately it will goes and it will pick up from here and it will put it over here. So that is why this is the way this index is work. Now, direct access method is one of the finest method, and you are putting everything, every data on that on a table, and you need not to go via primary key or via sequential method. So you are going directly. Suppose you are searching one particular book through the title, and you are just putting in the search box the name of the books, the title of the book. So it will goes directly to that particular tray or particular table, and it will pick up the same sequence, same terminology, which is located on that particular tray. So it could be a lakhs of data, it could be thousands of data, or whatever the data is. It will go directly and will pick up. So that's the direct access method of a data structure system, right? So this is one of the finest concept, and majority of the table and databases, they are using that particular database. Now, physical database designing. Data structure and file organization play an important role in physical database design. And physical database is a actual where there is no logical. It's actual data we're keeping over there. So that's why it's called physical database design. Now, in physical database design, they have the different queries and transaction, the files that will be accessed by query, the attributes on which selection conditions for query are specified. Where exactly you are meaning by query? Suppose you have a 3 table. I've already explained that. You have a 3 table, and one table is book table, one table is member table, and one table is circulation table. Now you have issued a book to a particular member in the circulation table. Now you are using query. Query, what you are going to do in the query, you are taking some important information from the book table, some of the important information from the member table, and you may take some information from the, suppose you are taking accession number and title of the book, and from book table, you are taking member ID and name of the member from the member table, and from transaction table, you are taking the due date of the book, and you are putting in one query, right? So that can be possible. It's basically query can be possible when you have a concrete physical layout of your data structure, right? And it's very efficient, and you can do some kind of deletion, addition on that, right? So here there are different attributes. The file that will be updated, the type of operation on each file, insert, update, or delete can be possible. The attribute on which the selection condition of a delete or update are specified. The attribute whose value will be changed by the update operation. Here the attribute are candidate for access structure, and attribute are candidate for avoiding an access structure, since modifying them will require updating the access structure. So these are the possible features of a physical data structure. Now, how we are going to analyzing the expected frequency of queries and transactions. That's very important. When you are creating a one databases, we'll take it very seriously in the database designing part. How we are thinking of different queries and transactions. You have to create different kind of attributes where through you can able to find out and you can to intuit yourself that how queries and transactions going to be done with these databases. Now, analyzing the time of constant of queries and transaction. This is some queries and transactions may have strained performance and constraint with respect to the response time. It is happened sometimes because when you have a different kind of attributes in the data structure, then it's create some kind of chaos in the query. So we need to rectify all this chaos. So then there will be probably there will be no problem in many databases which is available. Now, analyze the expected frequency of update operation. A minimum number of access paths should be specified for a file that is updated frequently, because updating the access path themselves slow the update operation. Many times you will find that your connectivity, or you are not able to access anything in your computer because the computer couldn't understand the path of that particular file. So it's become very slow. Sometimes it's not responding. So that's why we have to be very careful when we're creating some kind of path of one particular data. Now, based on the preceding information, one can address the physical database design decision about indexing. The attributes whose values are required in equality or range condition, selection operation, and those that are keys or that participate in join conditions, right? Here you can see some of the points to be kept, and while taking decision for indexing, the attribute which is to be indexed must be a key, or there must be some query that use the attribute either in a section conditions or in a join. An index can be made on one or multiple attributes. If multiple attributes from one relation or other involved together in several queries, multi-attributed indexing is warranted. Clustering index is possible, and it is also done in many of the database system when you have a different kind of, if you do not have kind of any primary key or kind of thing, so you can create a cluster. Then RDBMS, Relational Database Management, generally use B-tree way of indexing, right? Majority of the, you take SQL, Sybase, Oracle, even Access is always based on the primary key. Cluster index is possible in Access, but rest of the brilliant database, even SQL is also using B-tree. We have already seen some of the examples in MySQL with the B-tree concept. So these are the concept in your data structure.